Hey guys, chapter 10. This time we're going to do section 10.2, hypothesis test for a population proportion. So remember with hypothesis testing, it's going to kind of go hand in hand to our confidence intervals, meaning that our population proportion is going to use a normal distribution. Our mean is going to use a t distribution. And standard deviation and variance is going to use a chi-square distribution. So with all of that, let's continue. All right, so the politician hires a polling firm to obtain a simple or a random sample of 1,000 registered voters in her district and finds that 534 are in favor of the policy. So P hat, our point estimate in this case is going to be 534 divided by 1,000, which gives us 0.534. So do these results suggest that among all registered voters, more than 50% favor the policy? Or is it possible that the true proportion of registered voters who favor the policy is about 0.5, and we just so happen to survey a majority in favor of the policy? So even though it doesn't look like that much, we have 50% that we're looking at, that we're thinking, and our sample got 53.4%. So is this close enough to say 50%, or is it not close enough to say 50%? Is it something different? So that's what this section is going to be about. In other words, would it be unusual to obtain a sample proportion of 0.534 or higher from a population whose proportion is 0.5? What is convincing or statistically significant evidence? So with that, the observed results are likely under the assumption that the null hypothesis is true. We say that the result is statistically significant, and we would reject the null hypothesis. To determine if a sample proportion of 0.534 is statistically significant, we build a probability model. And since the sample data are from a simple random sample, we would have to test to see if it's if the product of n times p times 1 minus p is greater than 10, then we're able to use that normal distribution. In this case, the sample size is 1,000, so that's more than enough information to conclude that we have some sort of normal distribution here. And let's see, and that's sufficiently smaller than the population size, so we can use a normal distribution model to describe the variability of p hat. The mean of the distribution of p hat is going to be 0.5, which is what was stated back here. Where was it? So more than more than 50%, which is more than 0.5. Back here, 0.5. And the standard deviation of this distribution is just going to be this. So p times 1 minus p divided by n, and we take the square root of that, and that gives us our standard deviation for this. All right, so now with the sampling distribution of the sample proportion, remember what we're looking at is with our normal distribution, we have here in the middle the mean, and we go out one standard deviation, and that gives us, that's what these points right here are. So they calculated the mean as 0.016, and with 0.5, we just subtracted 0.016 and then added 0.016, and it gave us this distribution here. And now the logic of the classical approach. So we may consider the sample evidence to be statistically significant. So if the sample proportion is too many standard deviations, say 2 above the assumed population proportion of 0.5. So what we're testing is to see whether or not this data is actually holding the other data to be true. So this is what we believe. So we believe this to be true. So we believe this data here to be true. But what we're going to do is prove that it's true, prove that we might need some more data, or we have to conclude something different. All right, so we may consider the sample evidence to be statistically significant or sufficient if the sample proportion is too many standard deviations away, say 2 above the assumed population proportion. So remember, kind of wrapping everything up from the semester, we have 1 standard deviation away here, 2 standard deviations away. If you guys remember the empirical rule stated that 2 standard deviations away from the mean, we have 95% of our data. We could conclude something a little bit more, going 3 standard deviations away and saying that's 99.7% of our data. But just saying that 2 standard deviations away from our mean, we catch 95% of the data. That's one of like the more popular versions that we have. If we need to be a little bit more specific, we can. And by specific, I just mean like 99% of the data falling within those standard deviations. Let's see. So that's where this 2 came from. All right, next. Recall that our simple random sample yielded a sample proportion of 0.534. So remember, this was p hat, and what we're going to do is subtract p, or what we believe p to be. So here we have the mean of p hat, standard deviation of p hat. And because we are using a normal distribution, that's why the z-score comes back to haunt us. So the z-score is going to tell us where we are within all of this data. This is going to be our test statistic. And we're going to compare it to our critical value. So our test statistic, are we justified with saying that this is usual or unusual? So here we have this value of 2.15. So normally we would say that this is unusual because 2.15 is it's over 2 standard deviations away from the mean. So without having any other background information, we could say that this is an unusual score right here. All right, so with 2.15 standard deviations above the hypothesized proportion of 0.5, therefore using our criterion, we would reject the null hypothesis. So we would reject the null hypothesis because this is a very unusual, well, not very, this is an unusual value that we came across. But what constitutes an unusual value? Are we able to just say 2, or are we able to say something a little bit more? So why does it make sense to reject the null hypothesis if the sample proportion is more than 2 standard deviations away from the hypothesized proportion? What we're saying is that with 0.9772 probability falling within this category, within all of this shaded region, there's only a 0.2% chance, less than a 3%, way less than a 3% chance of this happening. So if we were out 2.15 standard deviations away from the mean, we're looking at that value being part of something way more drastic than what it really should be, right? So because it's way too out of the norm, we're rejecting that null hypothesis. So remember, our goal was to reject the null hypothesis and accept the alternative. So we're rejecting that null hypothesis. And let's see, so the area under the standard normal curve to the right of z equaling 2 is 0.228. And that's it. So if the null hypothesis were true, the population proportion is 0.5, then 97.72% of all simple random samples, or simple 97.72% of all sample proportions will be 0.532 or less, and only 2.8% of the sample proportions would be more than 0.532. So that's the way we're looking at these values again. All right, so now hypothesis testing using the classical approach. So if the sample proportion is too many standard deviations from the proportion stated in the null hypothesis, we reject the null hypothesis. All right, so the logic of the p-value approach. So the second criterion we may use for testing hypothesis is to determine how likely it is to obtain a sample proportion of 0.534 or higher from the population, whose proportion is 0.5. If a sample proportion of 0.534 or higher is unlikely, we have evidence against a statement in the null hypothesis. Otherwise, we do not have sufficient evidence against the statement in the null hypothesis. Again, all they're saying here is we have our null hypothesis and our alternative, or H naught and H1. There we go. H naught or H1. So our goal for this is always to find evidence to reject the null hypothesis, because at that point we can accept the alternative. We could say that this, I'm going to put a little heart because we end up wanting that. So we accept the alternative hypothesis and we're all happy because we did come to some sort of conclusion, whether it was a conclusion that we wanted or a conclusion that we didn't want. We still came to some sort of conclusion. If we are not able to reject the null hypothesis, we cannot say that the null hypothesis is true or H naught is true. So we have to kind of question everything that we have from here, because we do not want to accept the null hypothesis if the null hypothesis is incorrect. So that's all we're stating here. Next, we can compute the probability of obtaining a sample proportion of 0.534 or higher from a population whose proportion is 0.5 using the normal model. So the probability of p hat being greater than 0.534 is again equal to the probability. We're looking at the z-score. So this here is z is equal to all this data here. And we had already calculated this data right here. So that data ended up being 2.15. So we're looking at the probability of z-score being greater than 2.15. And the way that they got this data is they used Excel. So here, actually, let's start from the beginning with this problem. All right, so 0 point, we have x 543 or 5345 534, and in this case was 1,000. And we have p hat. P hat is equal to 534 divided by 1,000. That's how we got p hat. Then we could say 1 minus p hat is equal to 1 minus this value here. And now we would say that the mean is equal to, well, p hat, and the standard deviation is equal to, remember the standard deviation is equal to the square root of p hat times 1 minus p hat divided by n. So here it would be the square root. So square root of numerator inside the square root, we have p hat times 1 minus p hat close the parentheses for the numerator, divided by the denominator, which is n, and close parentheses for the whole square root. So we have this, and that's where they were getting all of these values. Then to find the z-score, actually, this wasn't the actual mean. We could say this one was x bar. And what we're claiming the mean to be is 0.5. All right, so now that we have that, we can find our test statistic or our z-score. And z is always going to be equal to x bar minus the mean divided by the standard deviation. And the standard deviation, we already calculated it to be the standard deviation for this sort of problem. So here, this is going to be equal to the numerator x bar minus the denominator, or minus the mean, close parentheses for numerator, divided by the denominator, our standard deviation. And this is where they got that 2.15. We rounded up a little bit, 2.16-ish. But that's how they found this value here. And now continuing on, the p-value is looking at the probability of p hat being greater than 0.534, which remember p hat is what we got this to be. So p hat being greater than 0.0534. And the way we could calculate that is equal to, with a normal distribution, what we're looking at, this is the area that we want, so greater than p hat equaling 0.534. But whenever we look at the probabilities, Excel only reads from left up to that point. So from the left, negative infinity up to that point, that's what we're going to find first, and then we'll find the probability here. So first we're looking at the probability of p hat being less than 0.534, and to find the probability of p hat being greater than 0.534, it's just going to be the complement. So here, equal to the normal distribution. So normal distribution or normal inverse. Do we need an area or do we have an area? This time, even though it looks like we have an area, we don't have any number here that we could use. So we're going to look for that area. So here, x is just this right here. The mean is this. Our standard deviation is this. Cumulative, we always want it to be cumulative, so that way it grabs everything under the graph. So this one's going to be true. Hit enter, and this is our data that we have. Now for p hat, this is for this red area, for this black area that we shaded here. It's going to be the complement, because all the red is, the complement of the red is going to be the black. So complement is going to be 1 minus this here. And there we go. So now what this value tells us, let's clear this out. What this value tells us, well, actually, there we go. So there is a, we could turn that into a percentage of 1.5567% chance that the population proportion is greater than 0.534. So these chances are very low So we would reject the null hypothesis of having the, so we would reject the null hypothesis stating that that the mean is greater than 0.05. So we would in fact just say that it's less than 0.05. All right, and let's see what these numbers are. So this is the same number that they got, 0.158. So the value 0.158 is called the p-value, which is about 2 samples in 100 will give us a separate proportion as higher or higher than one of the obtained if the population proportion really is 0.5. So because observed values are unusual, we take this evidence against a statement in the null hypothesis. And now a p-value is a probability of observing a sample statistic as extreme or more extreme than the observed under the assumption that the statement in the null hypothesis is true. So put another way, the p-value is like the likelihood or the probability that a sample will result in the statistics such as the one obtained in the statement in the null hypothesis being true. All right, and now hypothesis testing using the p-value approach. So if the probability of getting a sample statistic as extreme or more extreme than the one obtained in the smaller is small under the assumption the statement in the null hypothesis is true, reject the null hypothesis. So bottom line, the lower the p-value, the stronger the evidence against the statement in the null hypothesis. And these are just some of the conclusions that we could talk about. So the p-value being greater than 0.10, we're not going to reject it. So greater is going to, that looks terrible. So greater is going to be, let's say it's a right tail test. So greater than 10%, we're still looking at data that's somewhere over here. So we're not going to reject anything. We need a very small p-value in order to reject. So somewhere between 5% and 10%, there's some evidence. Again, they say the word some. So there's some evidence against a statement in the null hypothesis, but still not too crazy. Whenever we look at this data here, between 1% and 0.5%, so there's moderate evidence against a statement in the null hypothesis. Between 1% or between 5% and 1%, that was this one. This one here is between 1% and 0.1%. There is strong evidence against a statement. Anything smaller than 0.1%, like literally 0.1%, we would say there's very strong evidence. So that's just the way that we would say things. It's not, we're not considering it like this is the only way to say it, but we would just kind of state that we would want to say that we have very strong evidence if we do have very strong evidence, but we're not going to get any points docked off if it's not. All right, with this one, the figure illustrates the politician situation. So for both the classical and p-value approach, to hypothesis testing, the distribution of the blue or distribution in blue shows the sample or distribution of the sample proportion, assuming the statement is in the null hypothesis is true. The sample proportion of 0.53 is too far from the assumed population proportion of 0.5. Yeah, there we go. So therefore, we would reject the null hypothesis at the 0.5 and conclude that p being greater than 0.5 as indicated by the distribution in red. All right, now hypothesis testing about a population proportion. Okay, so from here, step 1, determine the null and alternative hypotheses. The hypotheses can be structured in one of 3 ways. Either a two-tail test, a left tail test, or a right tail test. So two-tailed test, we would have not equal to, or equal to and not equal to. Most important thing that we could note for all of them is that these are all equal to for our null hypothesis. So we're saying that the population proportion is equal to what we have stated. These other ones are going to be kind of brought on from the data that we have. So we either have not equal to, it being a two-tailed test. Left tail test is going to be less than, our population proportion is less than our point estimate. And our population proportion is greater than our point estimate. So that would be a right tail with that last one. Step 2, select a level of significance alpha, depending on the seriousness of making a type 1 error. Continue with step 3 through step 5, provided that the sample is obtained from a simple random sampling or data results from a randomized experiment, that the product of these sample size p hat and 1 minus p hat, the product of all three of those is greater than or equal to 10. And that these sampled values are independent of each other. So that is that the sample size is less than 5% of the population. Then we have two different ways that we could take this. We could either take the classical approach, so compute the test statistic, which is this value right here, and use table 5 to determine the critical value. And we would have these critical values for either a left tail test, right tail test, or two tail test. And for each of these, it would be just a little bit different. Again, for this approach, what we're doing is we're comparing the test statistic to the critical value. Test statistic is going to fall either outside of the critical values or inside the critical values. When it falls inside the critical values, then we would reject, we could call these blue areas like the rejection region. So if it falls within the rejection region, then we would reject the null hypothesis, but if not, we would just state it as such. Step 4, compare the critical value with the test statistic. So for a two-tailed test, it would fall within, if it falls within the rejection region, then we would reject it. So this looks a bit confusing, but all they're stating here is what I stated over here. If it falls within the rejection region, then we reject it. If it does not fall within the rejection region, then we do not reject. Step 5, state the conclusion. And if we're taking the p-value approach, so by hand, we would do step 3, compute the test statistic, and we would compute this here. Or we could actually do it a little bit different. We could have Excel find these values for us instead of comparing it to the standard normal distribution and then looking for it in the back of the book. As long as we plug it into Excel, we could actually find whatever that p-value is. And technology, we would kind of do this. So use statistical spreadsheet or calculator with the statistical capabilities to obtain the p-value. The directions for obtaining the p-value using the TI-84 plus calculators menu tab and all of that. We could actually find it in the book, I believe. But step 4, if the p-value is less than alpha, then we would reject the null hypothesis. And lastly, we would just state the conclusion. All right, so Humira, a medication used to treat rheumatoid arthritis in clinical trials for Humira, 705 subjects diagnosed with RA. So that means that N is equal to 705. Administered 40 milligrams of Humira every other week. So of those 705 subjects, 66, so X is equal to 66. Reported nausea as a side effect. It is known that the proportion of RA subjects in similar studies receiving a placebo who reported nausea as a side effect is 0.08. So that means that the mean is equal to 0.08. Does the sample evidence represent significant evidence that a higher proportion of subjects receiving Humira experience nausea as a side effect? All right, so that's going to help us with our null hypothesis, our H naught and H1. So the proportion is equal to 0.08, because remember, it's always going to be equal to in the null hypothesis or H naught. And H1 is always going to be either less than, greater than, or not equal to. So now looking at this as a sample evidence represents it. Significant evidence that a higher proportion, so P is greater than higher proportion of 0.08. Use alpha equals to 0.05. All right, so now that we have all of this, let's go ahead and go to Excel and input everything. All right, so we have N equal to 705. X is equal to 66. That tells us that P hat is equal to 66 divided by 705. Perfect. They wanted the mean. So mean, or not the mean, P, our proportion. Our proportion is 0.08, which means that 1 minus P is equal to 1 minus 0.08. And now that we have that, we could find our standard deviation. So now that we have that, we have our X bar. X bar is P hat, so equal to P hat. The mean is equal to P, and our standard deviation, it's equal to, so standard deviation is the square root of P times 1 minus P divided by N. So this is equal to square root SQRT of the numerator. So parentheses for the numerator, we have P times 1 minus P. And that's a numerator divided by the denominator is N. Close parentheses for all of that. And that's our square root. So now that we have that, we could actually, let's write down our null hypothesis and our alternative. So our hypothesis testing. So H0, and I'm going to say HA for our alternative, or for H1. Okay, so P is equal to 0.08. And for the alternative, P is greater than 0.08. So now that we have all of that, we could talk about the different approaches. So we have two different approaches that we have here, and that is the classical approach and also the p-value approach. So with both of these, there's two different ways that we could do it. So classical approach, we use our critical value and we compare it with our test statistic. All right, so now our critical value is going to come from a standard normal distribution. So what we're doing is we have our normal distribution here. We have our rejection region. So let's look at our hypothesis testing to see what kind of test we have. So P being greater than 0.8, notice that this arrow is pointing in this direction. So we're going to have right tail test. So with this right tail test, and now kind of looking at the rest of the data, we didn't write it down. So let's throw that right here. Because alpha, they did mention alpha equaling 0.05. So alpha was 0.05. And coming over here, alpha is this rejection region. So this rejection region is 0.05. And because we're using Excel, Excel is always going to look at the area to the left, not the area to the right. So when we come up with our critical value, we're going to look at this area here to get our critical value right here. So here, the critical value Z is going to be equal to a normal distribution. So normal distribution or normal inverse, do we have an area or do we need an area? For this one, we have an area, and this red area is going to be 0.95. It's the complement of 0.05. Because we're looking at the standard normal distribution for this, our mean is going to be 0. Standard deviation is going to be 1. Hit equals, and that's our test, our critical value. So now coming back over here, we have our critical value here. Z is equal to 1. What is that? 645. Could say that. And from here, with our classical approach, our test statistic Z, if it's in this red region, then we don't have enough evidence to state anything. If it's in this rejection region, so this alpha region, then we are going to reject the null hypothesis. So this test statistic comes from the actual Z, or the Z score of this problem. So we have Z is equal to X bar minus the mean divided by our standard deviation. And this is why we always benefit from having like a really organized data right here. So from here, our Z score, we could do equal to the numerator, we have X bar minus the mean, X bar minus the mean divided by the standard deviation. And now we have these two. So looking at these two values, if this value right here is 0.164, then our test statistic 1.33, it's not in the rejection region. So because we're not in the rejection region, we cannot reject the null hypothesis. So since our test statistic is not in the rejection region, we do not have sufficient evidence to reject the null hypothesis. So we do not have enough evidence at the alpha equaling 0.05 level of significance to reject anything. All right, so since we didn't have data here, we should get the same values over here with the p-value approach. But let's see if we get anything different. Let's clear this stuff out. Over here, so with the p-value approach, what we're looking at is a probability. Here again, it's going to be greater than, it's a right tail test. So what we're looking at is the probability of our p hat being greater than our test statistic being greater, or our mean being greater than our parameter, or yeah. So what we're looking at is the probability of, let's see. All right, so what we're going to do is the probability of p hat. Well, we're actually, hey, come on. I'm not sure why it's not working. There we go. Okay, so the probability of p hat being, remember, we're looking for this blue region. We're looking for that to be greater than or equal to or greater than what we have here. So 0.0936 or 0.094. But whenever we type it into Excel, it's not going to give us that one. So what we could do is find the complement. So P being less than 0.095. And we could find this one first, then find the complement over here. So equal to a normal distribution. So normal distribution or normal inverse. Do we have an area or do we need an area? So this time we need the area. Remember, the p-value is a probability of it being greater than or us falling into these rejection regions. So we're looking for an area. So here x is going to be the value that we're searching for. So p hat, the mean, we would just take the mean here, standard deviation, we take standard deviation. And lastly, cumulative, true because we want the entire accumulation of everything underneath the area under the curve. And if we put false, then it's going to be the opposite there. All right, so now that we have that, to find the complement is just going to be 1 minus whatever value we found, this value here. And now looking at this 0.09, and what we needed was 0.05 or smaller. So here it's going to be just the tiniest bit different, but we're still going to kind of have the same answer that we did here. So since our p-value is larger than our level of significance, we do not have sufficient evidence to reject the null hypothesis. So this one, our test statistic was not in the rejection region. Here, our p-value was not small enough. So again, we want something smaller. We want the probability to be smaller than our level of significance, our alpha. And because we didn't have that, we aren't able to say that that the data work for us in our favor here. So we would have to, if we were the people running this study, we would have to gather more information and see where these numbers ended up. But here, let's go back. All right, so step one, null hypothesis would be that the proportion of the subjects in the Humira who experience the nausea is 0.8% because the proportion of subjects taking the placebo who experience nausea. So remember, the null hypothesis is always a statement of no difference, so it's equal to. We want to determine if the sample evidence suggests that the higher proportion of subjects taking Humira nausea as a side effect is greater than. So we want to see if it's a higher proportion of them. So symbolically, the null hypothesis and the alternative are these here. All right, step two, the level of significance. So we have 0.05, alpha equaling 0.05. So the data results from a randomized experiment. This is something that we forgot to do, but we looked at the product of these three numbers. So n times p times 1 minus p. And when we multiplied all of those together, that product is greater than or equal to 10. And also, so about 1.5 million people suffer from RA in the United States alone. So we're well within 5% of the population, or less than 5% of the population. Step three, assume the statement in the null hypothesis is true. So P naught is equal to 0.08. So the sample proportion experiencing nausea in this case is 0.94. So this is our test, or not our test. This is our population parameter. This is our test statistic, our point estimate. We want to know if it is unusual to obtain a sample proportion of 0.094 or higher from a population whose proportion is 0.08. The test statistic here, they found the test statistic. We kind of did it right here. Actually, yeah, we did do it over here. And because this is a right tail test, determine the critical value at the alpha equaling 0.05 level of significance to be z sub alpha of 0.05. So whatever this value is here, that's the value that we found right here. So this was our critical value. From our critical value, it being a right tail test, this is our critical region, or we could call this our rejection region too. And because our test statistic, the one that we found, like our z-score, that value was lower than our actual critical region. So it wasn't in our critical region. So this is not a critical thing that we could do, right? We don't have enough evidence to continue with stating something to be either true or not true. All right, step 4 for the classical approach to test statistic, z sub 0. So our test statistic is labeled in the previous figure because the test statistic is less than the critical value. We do not reject the statement in the null hypothesis. So we do not reject our null hypothesis. Notice the test statistic does not fall into the rejection region. Note we will, or while we did not reject the statement in the null hypothesis of the proportion of Humira subjects experiencing nausea is 0.08, the p-value suggests that there is more moderate evidence to suggest that Humira users are experiencing an adverse reaction. So let's go ahead and finish this. So looking at the p-value approach, this might give us a different insight on the problem. We did all of this. So we want to know how likely it is to obtain a sample proportion of 0.094 or higher. Again, this is a value that we got. What we were trying to prove is that p is equal to 0.08. P hat ended up being almost an entire 1.5% above. So that's why we were kind of questioning everything. But here our test statistic, which we found earlier, 1.37, but for doing the p-value approach, we actually don't need it the way that we have to enter it into Excel. P-value approach, we're looking at the probability that p hat is greater than. So that's what we did here, p hat greater than. We couldn't find that one immediately, so we had to find this one first, the probability of p hat being less than 0.94, and we just looked at the complement here. They got something a little bit different because they estimated this, or they estimated their standard deviation, which forced them to estimate their z-score, which forced them to estimate this. So even though, so here we have 0.8, over here we have 0.9. So this is what we were actually looking for. So this is a value that we were looking for, and that's the value that we ended up getting. They got something a little bit different because they kind of cut a couple of corners. No big deal though. So from here, the p-value you can see it here, 0.091, 0.091. All right, so using Minitab, this is what they got. And step 4, the p-value 0.08 by hand, or 0.091. Means that if the statement in the null hypothesis, that is that p is equal to 0.08 is true, we would expect to observe 66 or more subjects who experience nausea in about 85% of 1,000 repetitions of the studies. The observed results are moderately unusual. So remember what we talked about, when alpha is more than 10%, then it doesn't raise any eyebrows. When alpha is less than 10%, that's when we start thinking maybe there is some truth to this. Maybe we could state something here. So that's why we use the p-value approach in this case, because here it looked kind of similar. It wasn't enough evidence to state that we could reject our null hypothesis, but over here we could see that less than 10%. So it's not an extreme value that we were looking at. It's still a moderate value that we could see here, but we still have some sort of evidence pointing to the contrary, that the value is greater than 0.8 or 0.08. Continuing on with this, we would expect to observe, okay, so the observed results are moderately unusual. However, because the p-value is greater than the level of significance, 0.05, we do not reject the statement in the null hypothesis. So this would be the frustrating part where someone, I'm guessing from the FDA or someone, whoever's running this study, if they're looking at this data, it's a little bit annoying because here alpha, we're stating alpha to be 0.05, but this is a very small level of significance. If we were to state the level of significance to be a little bit higher, or in this case, double, alpha equaling 0.10, then we would definitely be able to reject the null hypothesis and accept the alternative, but we're not. All right, so that leads us to this very last part. So there is not sufficient evidence at the alpha equaling 0.05 level of significance to conclude the proportion of subjects taking Humira who experience nausea is greater than 0.08. All right, that leads us to, I believe this is the last example that we're going to look at. So which do you think is easier to raise, a boy or a girl? When asked this question in 1947, 24% of all Americans said raising a girl was easier. So in June 2018, the Gallup organization surveyed 1,500 adult Americans. 1,500 adult Americans, of which 408 felt it was easier to raise a girl. Does this result suggest a proportion of adult Americans who believe it was easier to raise a girl has changed since 1947? Let's grab all the necessary data. Someone asked this question in 1947. P, oh, let's get a different color. P is equal to 24% or 0.24. Of all Americans said raising a girl was easier. June 2018, the Gallup organization surveyed N equaling 1,500 adult Americans, of which X equaling 408 felt it was easier to raise a girl. Does this suggest that the proportion of adult Americans who believe it is easier to raise a girl has changed? And we don't have an alpha. Maybe we'll get an alpha here in a bit. But from here, let's get our null and our hypothesis, our hypothesis test. So here we have H0, H1. Here we have the proportion is equal to 0.24. And we have the proportion something 0.24. And now let's look over here. Does this result suggest that the proportion of adult Americans who believe it's easier has changed? So here they're not stating greater than, they're not stating less than, they're just stating has changed. So this is not equal to, so equal to and not equal to. And now with that, we could take it to Excel. So now keeping all of this organized, we stated abruptly that this was 0.24. Next, we have N equaling 1,500. We have X equaling 408. That means that P hat, our point estimate, is equal to X divided by N. And now that we have that, we could state what our mean, our sample mean X bar, in this case is going to be equal to P hat. Our mean is going to be equal to what they stated earlier. And if this is P, we would need 1 minus P. One minus P, that's equal to 1 minus 0.24. and our standard deviation. Standard deviation is the square root of our numerator. So P times 1 minus P, and close parentheses for the numerator, divided by denominator, and the denominator is N. I think it's just because I forgot that I forgot that last parentheses. All right, so we have all of this. Let's state our hypotheses. So H naught is P equal to 0.24. HA is P not equal to 0.24. All right, so we have all of this. Let's clear it out. And let's see what our alpha is. So step one, null hypothesis will be that the proportion of adult Americans who believe that it is easier to raise a girl is the same as it was in 1947. So remember, the null hypothesis is always a statement of no difference. We want to determine that if the statement or if the sample evidence suggests that a different proportion of adult Americans is today believe it is easier to raise a girl. So this is a two-tail hypothesis test. And now with this, they stated the significance at alpha equaling 0.01. So let's just do this here. So alpha equaling 0.05 or 0.0, yeah, 0.05. And coming back here, we could get started on the problem. All right, so for this problem, we'll just go over the classical approach. We won't go over the p-value approach just because it's a two-tail test, a little bit more complicated, but no big deal. So from here, what we're going to do is take the classical approach. So again, what we're doing is we're identifying our test statistic and comparing it to our critical region. All right, just so we could kind of see what kind of problem we have. It's a two-tail test, so equal and not equal to, so that identifies a two-tail test. So we have left tail and a right tail. And since alpha is equal to 0.05, we're sharing 0.05 on either side. So this is half of 0.05, and this is the other half of 0.05. So this is going to be 0.025 here, 0.025 over here. And now with this, we're going to find these two values. So our z-score for the left side and our z-score for the right side. So looking at this value here, z of the area to the left of this value is 0.025. And on this value, the area to the left, not only are we getting this value here, but we're getting all of this region here too. So this region, in order to make it 100%, that would be 0.95 here. So the value here, the area to the left of this value here, 0.95 plus 0.025. When we add those together, we get 0.975. So those are the two critical values that we're going to identify right now. So we have z of 0.025, and we're also going to find z of 0.975. These values are coming from the standard normal distribution. So here, normal distribution, do we need an area or do we have an area? This time we have an area that we're looking for the associated z-score for. So here we're going to have inverse norm. Probability is going to be the area, so 0.025 for this one, because that's the one we identified here. The mean, because we're looking at the standard normal distribution, it's going to be 0, standard deviation of 1, and enter. That's what we have there. And we're going to find the same thing over here for the right side. So this one, again, is going to be a normal distribution, normal inverse, because we have an area. The area here is 0.975, mean 0, standard deviation 1, hit enter, and that's what these two are. So notice that 0.025 is just a negative 1.9. It's the exact same thing. This one's negative, this one's positive. And this just comes from our symmetry. So remember here in the middle, it's always going to be identified as 0 with the standard deviation of 1. Just a little play on fun stuff there. All right, so that's our critical values. And now that we have that, let's find our test statistics. So this is going to come from our z-score. So the z value for this problem. And again, z is just going to be equal to x bar minus the mean divided by the standard deviation. So equal to the numerator, x bar minus mu, and we're dividing that by our standard deviation. 2.9. So looking at this value here, if these values here are negative 1, or like this one's a negative 1.96, this one's a positive 1.96, this value of 2.9 is going to be like way over here. So clearly in the rejection region. So let's cancel that. So we could come right over here. Actually, we could keep this up just so we could see it. So since we are in the rejection region, since our test statistic is in the rejection region, we have sufficient evidence to reject the null hypothesis. So at the 5% level of significance, we have enough evidence to reject the null hypothesis and accept the alternative. So we would end it with saying there is a difference in the percentage of adult Americans that believe that raising a girl is easier. And you could just state it as that. And that's it. So I know there is more data that there are more examples in this homework that you guys could work on, but for this chapter, I feel like that's more than enough information for one chapter. I'm sorry, for one section. So if you guys have any questions, go ahead and email me, but if not, good luck on your homework. Bye.